time period of satellite. So first of all, let me give you the definition of time period. The time which is taken by the satellite to complete one revolution around the earth is called its time period. That is T, or it is also known as periodic time, or the period of revolution. So any one of these three words you can use for describing the time period. Now during this time, the distance traveled by the satellite is equal to the circumference of the circular path. And the circumference is denoted by 2 pi r. And therefore, if I want to find out the orbital speed, and speed is distance covered divided by the time interval. So here the distance covered is 2 pi r and the time interval is capital T, and therefore the orbital speed I am denoting as VO is equal to twice pi r divided by T. So this is my equation number 1, and with this equation I can substitute the values If you remember this equation, mv0 square over r was equal to gme into m over r square, and therefore m over r into v0 square means 4 pi square r square over t square is equal to gme into m over r square. Now by cancelling the value of m on both the sides, we will get the equation like 1 over r 4 pi square r square over t square is equal to gme over r square. And here 1 r will be cancelled out in the denominator. Therefore, now I am making this t square as an object. Therefore, t square is equal to 4 pi square. Here r square and this r will come into the multiplication. So here r cube divided by gme. Now in this particular equation, some of the terms are constant. See, this 4 is constant, pi square is also constant. The value of universal gravitational constant and the mass of the earth is also constant. Therefore, the constant terms I am putting into the bracket, so it is 4 pi square divided by g into me into r cube, and therefore I can write down this particular equation in terms of proportionality as t square proportional to r cube. So this equation refers to Kepler's third law of orbital motion, and using this statement I can write down Kepler's third law of motion, which is now related to the orbital motion of satellite. Then the square of the orbital time period of the satellite is directly proportional to the cube of the orbital radius. And here there is a specific meaning to write down orbital radius, because we have to distinguish this term with respect to radius of the earth. Now recall this equation. This is equation number 3, and this particular statement is known as Kepler's third law. Now, from equation 3, I can get square root on both the sides. So, my equation for time period t is equal to 4 pi square r cube divided by g into me whole raised to 1 by 2. And that is equation number 4. And with this, we have obtained the equation for time period of the satellite. Now, we will switch on to consider two different types of satellites. Let's start to study about these types of satellites. So here is the first type, geostationary satellite. So which kind of satellites are falling into this category? So it is basically the satellites of Earth having their orbital periodic time of 24 hours are called geostationary or geosynchronous orbit or geosynchronous satellite. So basically the time period of this satellite is equal to the time period of Earth. That is 24 hours. Now, the word stationary has been used because this satellite appears stationary as viewed from the Earth. So whenever you watch this kind of satellite and you are taking the observations from the Earth, then such kind of satellites are appearing to be stationary. Such a geostationary satellite revolves around the Earth in the equatorial plane from east to west direction. So, they are moving in the orbit. Which orbit? Equatorial orbit. And direction is east-west. And such kind of arrangement I am giving you in terms of figure. So here is the arrangement is shown and some quantities which I am writing over here for geostationary satellites. So first of all, the mass of Earth will be as it is, that is 5.98 into 10 to power 24 kg. Here basically we are going to find out the height of geostationary satellites. This h is our target to find out, and if I have the value of this r and then this re is known, radius of the earth. Radius of the earth is 6400 kilometers and we have all other values. So it is necessary that we should find out the value of this small r, and in order to find out the value of small r, I can directly put in the equation of time period by using this me value. What are the other values? Universal constant g, that is having the value 6.67 into 10 to power minus 11 Newton into meter square per kilogram square. And the time period you can easily derive. The time period will comes out to be 24 hours, but you have to convert into the second. So it is 24 into 3600 seconds. Now, by putting all these values in the equation of time period t and making the object as r, we will get 42,260 kilometers. So at this much distance from the center of Earth, the satellite is moving in the equatorial orbit, which is actually having the shape of ellipse. And here you can see from the direction east to west it is rotating. Now, as per the equation, r is equal to re plus h, substituting the value of re. But r is equal to re plus h. Here the value of r is 42,260 is equal to the value of re is, what is the radius of the earth? 6,400 plus h. So from this now I can find out the value of height h minus 6400. So we will get about the answer 35,860 kilometers, which is nearly, you can take about 36,000 kilometers. So at this much height, there is existence of geostationary satellite, and this satellite cannot remain geostationary for any other height except this one. So what are the application of geostationary satellite? So the application of geostationary satellites are mostly for telecommunication. And also it is all most useful in the application of GPS, and GPS is the acronym of Global Positioning System. So this is basically the system which comes into your mobile phone devices, or some particular device which provide only GPS are also now available. And this particular technology, GPS technology, is useful to find out the map of a particular destination, and it is very useful in the traveling. Now we will see the another kind of satellite, that is polar satellite. So this kind of satellites are revolving around the earth in the north-south direction. Their height from the surface of the earth, means the value of r is given over here, is 800 kilometers. So it is basically not so much far off the earth, and you have to add plus RE, then you will get the actual value of R. So it is around 7,200 kilometers from the center of the earth. Now since the earth rotates in east-west direction, these satellites can view every section of the earth many times in a day. So this is one advantage of polar satellite. And similarly, with the help of a camera, which is inside the satellite, it can see a thin strip of the earth in every rotation. So this is basically the use of camera which is inside the satellite. Now in the next rotation, it will see the region of the next strip. So suppose this is the, I am taking one cross section of the earth, and suppose the camera inside the satellite had seen this kind of thin strip in its first rotation, then during its next rotation, it will see the next thin strip in the second rotation. And so it can see the entire earth many times a day. They are useful in remote sensing. Also in meteorology, environmental study, So all these are applications of polar satellites, and as it can see each part of Earth in many times a day, so it is very much useful in spying. So these are the applications. Now we will see the actual construction of polar satellites or the motion of polar satellites. So here is the polar orbit is shown, which is from north to south, and its rotation axis is in this direction, and this is known as polar orbit, and this is our Earth, which is we can consider as equatorial orbit. And that's why Earth is also rotating, this orbit or the satellite in this orbit is also rotating. So each part of the Earth can be seen by the help of this satellite many times in a day. And now this is the end of all the theories of this chapter. So now we will solve the remaining illustration.